Hello, welcome to my presentation. I am Sanjoy Basak from University of Minnesota. Today, I'll present the final project report for EE 5940, Special Topics in Electrical Engineering 1. The title of my presentation is The Design and Simulation of Charge Pump Phase Lock Loop PLL in LTSpice. Since the PLL architecture is a charge pump one, that is an analog one, it has four major components: the phase frequency detector, the charge pump containing this phase frequency detector or PFD, a voltage controlled oscillator VCO, and finally a divider. The PLL is fed by a low frequency crystal oscillator at 100 MHz. However, the target of the PLL is to synthesize a higher frequency for useful operations. For example, PLL may be used to synthesize LO frequencies for an RF mixer. The VCO is the main component which generates this high frequency output, while the rest of the loop ensures that the VCO frequency does not drift away from the desired high frequency and stays locked to where it is supposed to. The very first block in the PLL is the phase frequency detector, or PFD in short. The PFD has two inputs. The main function of the PFD is to detect any difference in the phases or frequencies of the two input signals. It has already been discussed in the textbook in great detail that having only the phase detector is not sufficient, since any signal may very well get locked to any of its higher order harmonics. Hence, we need both phase and frequency detector. Structurally, the PFD is composed of two resettable D flip-flops. C1 is the input to one D flip-flop, while C2 is the input to the another D flip-flop. Up is the output to one D flip-flop, and down is the output to another D flip-flop. These two D flip-flops are synchronized by the condition that both cannot output high simultaneously, meaning up and down cannot go high at a time. If, however, up and down goes high at a time, reset signal will be triggered, this one, and both flip-flops will be reset instantly. Now, there's a charge pump that charges up or discharges down a load capacitor. The PFD we just discussed is at the heart of this charge pump. If the up signal from the PFD is high, the charge pump will charge up the capacitor, or if the down signal from the PFD is high, the charge pump will discharge the capacitor. The bias current flowing through the cascaded inverter is used for charging or discharging operation. This bias current is generated by the current mirror on the left hand side from 5 microampere seed current on the left side of the diagram. As we know, for the PMOS to turn on as up signal goes high, there has to be an inverter following the up signal, because a zero will actually turn on a PMOS. However, to match the delay due to this inverter, an always turned on transmission gate is used following the down signal. In our work, the charging current is close to 0.9 milliamps, and the charge pump load capacitor here is 200 picofarads. In this slide, we show the operation of the charge pump when it is charging up the capacitor. Every time the up signal is on, some current will flow into the capacitor. The down signal is on for a very short period of time, a very short moment, and gets resetted instantly, so we don't see down signals effect that much. Let's calculate the average slope of this charging operation. In this equation, which is mentioned here, del phi in is the phase difference between the two charge pump inputs. The more the difference, the steeper the slope. We have calculated this slope from this equation to be 1.1125 millivolts per nanosecond, while the slope we measured from the actual plot that's been shown in this slide, we have measured the slope from the real plot to be 1.075 millivolt per nanosecond. So they are almost equal. Similarly, I have verified that during the discharging operation, the downward slope is also equal to what we expect from our equation and calculations. So followed by the charge pump, the next block of significant importance is the voltage controlled oscillator. Now, the main reason we are charging up or discharging down the load capacitor is to create a voltage on it, which in turn will be used to control this voltage controlled oscillator VCO. The VCO has a differential structure with LC load or LC tank as we call it. Its free running or resonance frequency is given by the equation F oscillator is equal to 1 upon 2 pi square root LC, which is equal to 1.6 gigahertz because I designed this for 1.6 gigahertz. And here we have chosen an inductance of 5 nanohenry and a capacitance of 1.88 picofarad on each side, left and right. As we can see in the figure, the V control VCTRL signal is used to set up the voltage level on the other side of the varactor. So by changing the VCTRL voltage, the varactor capacitance can be changed, which in turn will tune the VCO output frequency. That's why it is called the voltage controlled oscillator in the first place. So on the bottom, the cross-coupled NMOS pair creates positive feedback which oscillates. However, in a SPICE simulation, unlike in real world where we are there are plenty of noise coming from resistance and wiring resistance, etc. In the simulation, it's ideal. We don't have that. So we have to artificially inject additional noise source to trigger this oscillation initially, which we supply from the VDD side. The tail current at the bottom is again generated from the seed current of 5 microamps using a current meter. So designing a good current meter with good enough dummies to match both sides is obviously important. Now let's see how the VCO output looks like. If we take the FFT of the VCO output signal, then we get the peak at the resonant frequency, which is in this figure 1.6 gigahertz, and which is exactly what we calculated, exactly what we designed for. We should mention here that when we calculated the oscillation frequency from the LC equation, the C, the capacitance, not only includes the fixed capacitance but also includes the varactor capacitance, which is tunable. Therefore, we might have to go back and forth a couple of times to obtain the desired resonance frequency that we're looking for. If we do not know the varactor capacitance for a particular two-terminal voltage in the first place, which we do not, so we have to go back and forth to fix that. Maybe once or two iterations should be fine. Another interesting thing that we can see from the figure is that this 1.6 gigahertz does not have any even harmonics followed by it. It only has the odd harmonics. This is expected because all the even harmonics gets cancelled by the differential structure, and we can only see the peaking at the desired frequency and much low gain peaking at the odd harmonics here. So let's now go to the next slide. This is an important slide characterizing the VCO tuning. So we sweep the VCO control voltage VCTRL on the x-axis, and we see how it tunes the varactor capacitance and in turn the resonant frequency or free running frequency of the VCO. As we can see from the plot, sweeping VCTRL from 0 volt to 1 volt, we can tune the center frequency from around 1.613 gig all the way down to around 1.590 gigahertz. So this is fairly a narrow range, I would say, around 14 megahertz or so. So now this narrow range also puts constraints on the locking range of the PLL for sure. Now 24 megahertz range at center frequency of 1.6 gigahertz translates to a range of 16 times less or around that at 100 megahertz center frequency. Also, when VCTRL is at VDD over 2 or 0.5 volt or 500 millivolt, the oscillator frequency is exactly at 1.6 gigahertz, meaning that we are keeping the provision for the PLL loop to drift either way and get corrected by tuning of the VCTRL. Finally, our last block and nevertheless very important block is the divider. The divider function is very straightforward. It divides the high frequency VCO output 16 times to bring it down to 100 megahertz and then feeds back to the PFD input or charge pump input. When a D flip-flop's Q bar output is fed back to its D input, the DFF produces output signal half the frequency of the input clock. So to obtain 16 times reduction, we simply can create a cascaded chain of 4 such feedback connected D flip-flops. So it's very important to note that the choice of the D flip-flops is important since it may be a vital component in the overall power consumption of the system. So this rigorous analysis of power consumption by different sorts of D flip-flops has been done by Professor Eric Klumperik in this reference, which was published in ISCAS 2011. Here, Professor Klumperik have shown that among all different D flip-flops in terms of power consumption as well as jitter reduction, the dynamic transmission gate based D flip-flops are the best. They do not consume any static power, they only consume dynamic power. And for our design, we are following this reference and following this energy efficient D flip-flop structure. Now I am very excited to share this very interesting thing. This is that so when the VCO oscillates, it oscillates around a DC offset of 1 volt or VDD. However, we need to feed the divider block with rail to rail signal, a signal that bounces between 0 volt to VDD. We have 1 volt VDD here. So this signal having 50% duty cycle at 1.6 GHz or around will have an equilibrium or average at VDD over 2, that is 0.5 volt. This means we need to change the VCO output DC level from VDD at the VCO output to VDD over 2 before we feed this back to the divider. Since the frequency here is high, AC coupling capacitors can be used. So we can use AC coupling capacitances. And now following this AC coupling, which transfers this small signal at high frequency, DC level has to be set. Now DC level can be set by resistive divider that we have done here, we have shown here, but this can also be set by resistive feedback simple inverters only, which will not only set the DC level but also will provide some gain. Here we don't need the gain, we just need the DC level. And also by using resistive feedback connected inverter for setting the DC level, we can actually reduce the power consumption to a much larger extent. But due to time constraints, here I have implemented only resistive divider to set the DC level to VDD over 2 at the output. So both resistances are same, and we are doing it differentially for both the output P and output N, both paths. Interestingly, we have to keep in mind that now a CR high pass filter is formed. We need to choose the C and R values very carefully. We need to choose them such that, one, there is sufficient AC coupling of the VCO output signal, and two, the CR high pass filter has cut off above the VCO output frequency, which is 1.6 GHz in this case. So this we have to be careful of, and we have chosen this carefully as reported in the report. And we also wanted to show the divider simulation results at the very output of the block, which is 100 MHz, as we expect if we do not tune the VCO output from its equilibrium position that much. This signal now goes into the PFD input and locks to the crystal oscillator 100 MHz clean output, and this locks at a fixed phase difference. We'll show that shortly. So this is the output of the overall divider block. So if we think in terms of D flip-flops, this is the output of the fourth D flip-flops in the cascaded chain. Let's now show the and discuss the overall PLL simulation when in lock. So the PLL works perfectly when the reference clock is 100 MHz. In this plot, the green and red waves show the PFD input. They are not drifting away from each other. So this means that they are in lock, since there is nothing changing to move them from the locking condition. And let's now see in the next slide what is the condition of VCTRL, what is the value of VCTRL, how does it change when the lock is achieved. As the PLL starts running, the VCTRL moves up from 0 volt, initial 0 volt, and after some time it gets almost stabilized at some higher voltage level and doesn't move from there. Now this is the ideal condition. Both inputs of the PFD has exactly equal frequency and a small yet constant phase shift between them. Yes, we understand that VCTRL is noisy. The noise is mostly attributed by the dynamic current consumption in the divider D flip-flops. In practical silicon implementation, digital and analog power supplies are kept separate to avoid such noise. But here we have supplied both digital and analog blocks through the same VDD as instructed to calculate the overall power consumption easily. But this is giving us some noise. Yet from the average level, we can see that after running this for a long period of time, it stabilizes. I have just given a screenshot for not so long period of time, but if I run it for much longer, then it actually stabilizes at a certain level, giving us the scenario at which CTRL is fixed and the phase difference between the PFD inputs are also constant. So what happens if PLL is not locked? This is shown in the slide. If the input frequency of the PLL is much away from the designated 100 MHz, then the PLL won't lock if they are much different, the both PFD inputs. This means the two inputs of the PFDs are away from each other by a large amount. This difference in frequencies should result in a very low bit frequency between them, which is the difference between their frequencies. Interestingly, this bit frequency is visible as long periods in VCTRL signal, which is shown in red here. So VCTRL is not stabilizing at a particular value, rather oscillating at a very low bit frequency. In this example, we have moved the reference frequency around 20 MHz away from its 100 MHz initial value, and the PLL is here is out of lock. They are not locking, they are creating low frequency bits. Finally, we want to show the performance summary. My designed PLL has a center frequency of 1.6 GHz and it consumes an average current of 4 milliamps at 1 volt VDD supply, which means 4 milliwatts of power. Therefore, the figure of merit FOM from the given equation is 1.9382. One comment I would like to make is that the PLL center frequency could have been made much higher with LCVCO. However, the narrow locking range was the reason why we wanted to keep this synthesized high frequency much lower than what we can design for. Finally, the references that we have used, we have mostly utilized charge pump, PLL blocks and sub-blocks from designs in the book. The most power efficient D flip-flop has been used from Professor Eric Lumpering's paper in reference 4. Also, we have indicated and we have also mentioned in the report that on-chip capacitances, which has this is a patent from our university. So on-chip capacitances can be made very dense, but inductors occupy largest amount of area in an LC tank. So minimizing inductance and maximizing capacitance can be a target for the LC tank. However, if fixed capacitance is made much larger, then the varactor variation will have smaller impact on the VCO frequency tuning. So a trade-off definitely exists. I think that's all what I wanted to present today. Please let me know through email if you have any questions about any part of my design. Thank you.